Hey everybody, we're back for the second half of the lesson we started in the last video. If you remember, the last video we were working on this example from our notes. Today we're going to finish up here on the back. So what number 5 says is, using geometry, find the exact area trapped between f of x and the x-axis on the interval from 1 to 4. Okay, since it's a linear function, we can do just that. So again, I'm just going to sketch this out. We have our x, our f of x. We're going from 1 to 4. We know that when we plugged in 1 to our function, we got 8. And when we plugged in 4 to our function, we got 2. So we were here, and that was linear. We dropped our sides down here. And so we are now going to use geometry to find the exact area. So the shape that this forms here, of course, is a trapezoid. Four-sided figure with one set of parallel sides. The parallel sides being here and here. This is going to form our bases. So the parallel sides of a trapezoid are called our bases. So this will be base 1, this will be base 2, and the distance between those two bases forms our height. Okay, so the area formula for a trapezoid, if you remember from geometry, is 1/2 times your height times the quantity b sub 1 plus b sub 2. So for us in this particular example, half of our height here is 3 units, 1, 2, 3. The distance between 4 and 1, so 3 units. Our bases are 8 units and 2 units, so we'll add those together. So we're really finding 3 halves of 10, which is 30 halves, or 15. So the exact area of this region is 15 square units, which is exactly what we got on the previous side for the midpoint rectangle. So we've learned something here. When your function is linear, midpoint rectangles will actually find exact area as well. Okay, number 6 is a bit of a review. It says, using Riemann sums, find the exact area trapped between f of x and the x-axis on the interval 1 to 4. So instead of appealing to geometry, we're going to appeal to good old calculus and our good friend Riemann. So here we go. We're going to start with the formula, the limit, as n approaches infinity, of the sum from I equals 1 to n of f of x sub I times delta x. You all know I go immediately to my side work, where I find 3 things. I find delta x. Delta x is b minus a over n, or 3 over n. Step 1. Step 2, I find f of x sub I. Well, since f of x is equal to negative 2x plus 10, f of x sub I is equal to negative 2x sub I plus 10. Finally, I find my x sub I. X sub I is equal to a plus I times delta x, which I will rewrite as 1 plus 3i over n. I'm going to take all of this information back up to my formula, so my next step will be specific to my problem. Limit as n approaches infinity of the sum from I equals 1 to n. Okay, here's my f of x sub I. Now what I'm going to do is bring that up, but I'm also going to specifically plug my x sub I in here for x sub I. So it's going to look like this. Negative 2 times the quantity, 1 plus 3i over n, plus 10, and this is all going to be multiplied by my delta x, which is 3 over n. Okay, my next step is going to be some algebra, and I'm going to skip a few steps here, because you can see I only have a limited amount of space. So one thing I can do, I'm going to distribute here, of course. I'm going to take the negative 2 and distribute it. But what I can do all at the same time is negative 2 times 1 is negative 2. Negative 2 plus 10 is 8, and 8 times 3 over n is 24 over n. Okay, I'm going to do the same thing with the second part. Negative 2 times 3i over n is negative 6i over n, times 3 over n is negative 18i over n squared. Now, you don't have to skip all those steps, but I'm going to do it because I have limited space. My next step is to use one of my sigma rules to split up my problem into 2 sigmas. So I'm going to have my 24 over n here, and then I'm going to repeat it with my 18i over n squared. I am now going to work on this part. Now, I know that 24 over n is a constant, and I know that the sum from I equals 1 to n of a constant is just n times c. Well, since n times 24 over n is 24, I have the limit as n approaches infinity of 24, which is nothing more than 24, minus. I'm going to bring down my limit here. I'm going to pull 18 divided by n squared, which is my constant, to the front of the sigma sign, and I'm going to leave my I trapped alone inside. My next step, I'm going to replace the sum from I equals 1 to n of I with what it is. This guy right here means the same thing as n times n plus 1 over 2, which is n squared plus n divided by 2. And then I'm going to multiply these two fractions. So I'm going to have 24 minus the limit as n approaches infinity. I'm going to distribute 18, so 18n squared plus 18n all over 2n squared. And now I have a limit. The limit here, if I plug infinity in, I'm going to get infinity divided by infinity, which is undefined. So from our work in Chapter 2, we know that to go on with the limit approaching infinity, we divide each term by the highest power of n in the denominator. So this is going to result in 18n squared over n squared plus 18n over n squared all over 2n squared over n squared. I'm going to come up here. I'm going to reduce. So I have 24 minus the limit as n approaches infinity. 18n squared divided by n squared is the constant 18. 18n divided by n squared is 18 over n. 2n squared divided by n squared is just 2. Now I can plug infinity back in for n, and it will result in this 18 over infinity, which will head towards 0, leaving me with 24 minus 18 divided by 2, 24 minus 9, 15 units squared. And so Riemann has just confirmed the geometry we did earlier, which also confirmed the midpoint rectangles. Okay, final part, number 7. This is brand new. Using the fundamental theorem of calculus, find the exact area trapped between f of x and the x-axis on the interval from 1 to 4. Okay, fundamental theorem of calculus. We are so going to get into this in the next few days. For today, I just want to show you the mechanics of the fundamental theorem. It is the shortcut to Riemann. It is, in today's lesson, it's a skill. It's something you're going to do, but it does not make sense today why you're doing it. So let me show you what it looks like, and the why will come later. So what you do is, you're going to draw this S symbol that we drew several days ago when we learned how to anti-differentiate. You're going to put your function inside of it, negative 2x plus 10, followed by that dx we put on the end. So remember earlier, in earlier lessons, I said, just draw the s, just put the dx. Don't worry about y, we'll get to that later. Okay. Now, one thing we're going to add to this is our interval. Since we're going from 1 to 4, we're going to write the 1 here at the bottom of the S symbol and the 4 at the top. Now, just a little preview for future lessons. Since this looks like an S, and sigma is the Greek letter S, kind of thinking these have something to do with each other, I think we're finding the sum. As we go from 1 to 4, of what's going on in here. Well, if you take a look at this, you see the multiplication here. Here we have change in x, and here we have f of x. so it seems to me we're finding like the base times the height of some rectangles, and we're summing those areas up, length times width. I don't know, maybe, maybe not. But here's what we learned how to do. So when you see this S symbol, you learned from me that you anti-differentiate. So the antiderivative of negative 2x, well, we're going to add 1 to the exponent, and we're going to divide out front by that new exponent, and negative 2 divided by 2 is negative 1, plus 10x plus c. And that's where we used to stop. But today, we're actually going to put a bracket on our right-hand side, and we're going to bring those boundaries 1 to 4 along. Okay? The next thing the fundamental theorem of calculus will do is it will take your upper bound 4, and you will substitute it in for these x's. So negative 4 squared plus 10 times 4 plus c. And then you will subtract, plugging the 1 in. Negative 1 squared plus 10 times 1 plus c. And then you will evaluate. So doing the math here, we're going to have negative 16 plus 40 plus c minus negative 1 plus 10 plus c. This is going to give us 24 plus c minus 9 plus c. And when we distribute the negatives through the back quantity, we're going to have 24 plus c minus 9 minus c. Those c's are going to drop, and you're going to be left with 15. Coincidence? I think not. Now again, you don't know why this is working. Like, why are we subtracting? Why are we plugging the top in minus the bottom? That's going to come later. For today, I just wanted to show you that there's yet this other way, much shorter than Riemann, that will help us to also get that same answer.